Good morning, HVAC team. So today we are going to start Mod 155, which is commercial refrigeration systems. We're going to start off in Unit 16, which is about evaporators. So let's go ahead and jump into that. So a quick review on evaporators. All of you should know the function of the evaporator. I know personally that a lot of you do, but for those who don't know quite what they do, the evaporator is the portion of the refrigeration system where the heat energy is absorbed from the product or from the conditioned space. So we all know that as far as airflow goes, we have two types of airflow in the refrigeration system. We have as far as the inside goes, you still got the condenser, which also needs plenty of airflow. But you have the return air and you got the supply air. So the return air is where the air in the room is being sucked out of the room into the system. That air is getting blown across the evaporator coil, and then it's coming out of the other side of the evaporator coil, which is the supply side, and it's coming out as conditioned air. So what's happening at the evap coil is that the heat energy in that return air is being transferred because the second law of thermodynamics says that heat energy travels from hot to cold. So that warm air, all the heat energy in that warm air is now going to want to go into that cold refrigerant, which is inside of the evap coil. So if you got 40-degree refrigerant in there, you got 75-degree air coming across there. All that heat energy is getting absorbed into that refrigerant. And then that same heat is going out of the evap coil through the suction line back into the compressor and then out into the condenser where it is released outside. So that's where the heat goes. The heat is absorbed in the evap coil. And so that same warm air that initially came into contact with the evap coil is now coming out of the other side cold because all the heat energy that was in that air was absorbed into the evap coil. So now it's coming out of the other side cold, and you got your nice 55-degree supply air, and that heat energy that's now in the refrigerant is headed out to the compressor where it's going to be compressed and then shot out into the condenser where it's then going to be transferred into the ambient air outside where we don't care. So we're taking the heat from where we don't want it, we're dumping it outside where we don't care. So, and the evap, its role in that process is absorbing the energy, the heat energy from the air or from the product in refrigeration, because the product could be produce or meat or whatever is inside of that box. So in air conditioning, my background is all air conditioning, mostly air conditioning. I'm not going to say all. I have done some refrigeration work, but mostly air conditioning. So the product is us. It's comfort cooling. So we're trying to cool the space where people are occupying, whether it be office space or at home. So anyway, so that is the function of the evaporator. So let's jump into Chapter 16. The objectives for Chapter 16 are identify the 4 broad categories of evaporator applications, discuss the concepts of sensible and latent cooling as they relate to evaporators, explain how bypass air and dehumidification work, list the types of water cooling evaporators. Also explain the difference between flooded and direct expansion evaporators, explain the purpose of the condensate drain trap in air conditioning evaporators, list the 3 common types of defrost in commercial refrigeration systems, and discuss the importance of using an evaporator coil that is an AHRI match to the condensing unit with which it is used. So here's a few different types of evaporator coils. So you have the bare type, which doesn't have the fins on it. The plate type, you'll see more commonly in like refrigerators. And then the tube and fin, this is the most common that you'll see in air conditioning, commercial air conditioning, residential. And then you have the 4 different configurations. So these are the only 4 different configurations that I think that comes up on like a review question or an exam or something. But these are the different types. I'll go ahead and make it a little larger and then lose my place because I don't know how to exit from this screen without going back to the beginning PowerPoint, but I'm working on my technical savvy. But anyway, so this is the slab coil. This is a commercial coil all day long. Most of them are going to be like this. When you're talking larger units, 10 tons or above, usually going to see those big slab coils. Then over here, you got your slant coil, which you also see in commercial a lot of the time. And then here you got your A coil, which is more often seen in residential. Almost every residential unit that I've worked on had an A coil, which is this configuration, and they're usually upflow or horizontal flow with the return air coming in this way and the supply coming out of that side. And then over here you have your N or M coils, where there's just a lot more circuits, but still doing the same thing, just a larger capacity. Okay, let's go back and find my place again. All right, so coil airflow direction. So these are the 4 different airflow directions. You got upflow. I will zoom in again. So this will be upflow. So that's your A coil there, and your blower motor in this case is located above the A coil and is drawing in the return air through the bottom of the A and then coming out through the top. And that will be your upflow. And then downflow is the opposite, obviously. And then you have horizontal flow. So horizontal flow. And then you have multi-position, where there are coils that you can use horizontal or upright in a upflow situation. You have to pay attention to that though, because the ones that are multi-position, you can have it upflow or you can lay it on its side, but you can only lay it on one side. Usually it'll be horizontal left or horizontal right. I think there are some that you can change it, you could go left or right, but a lot of the time it's going to be horizontal left or horizontal right. And the reason being is that there's a drain pan on one side. So if you stand it upright, there'll be a drain pan below the coil, and then there'll be another drain pan on the side of the coil, allowing you to set it on that side. Or if that drain pan is on this side of the coil, then you can set it on that side. So that doesn't always get you into trouble, but it happened to me once where it was a horizontal left and I installed it as a horizontal right and did not realize until I had already installed it that my drain pan was on the top of the coil rather than on the bottom, which makes absolutely no sense because gravity is going to pull all that water down. It's not going to go up and into my pan and not flood the attic. It's going to fall. So all that condensation would have just started to collect inside the unit and leak out of every crevice it possibly can to flood out the attic. So I had to turn that coil around. You might ask yourself, well, why not just spin the entire unit around? That would have been easy to do if I had paid attention before I installed it. But now all my ductwork is in, all my piping is in, all my electrical is in. So to turn the unit around would be to completely redo the install. I got my supply plenum on this side. I got my return plenum on this side. I got my piping and my wiring over here. It was easier to just pull my refrigerator back out, cut my lines, flip the coil over, and now the entire unit is facing me, but the coil is facing that way. So it was a pain. It was a bonehead move. It was a little embarrassing, but after the fact, it's not so bad because all your maintenance calls and your service calls are usually going to involve opening the furnace compartment. You don't really typically open the coil compartment unless you're leak checking or something. So the fact that the rest of the unit was still facing me made it not so bad, but I had to flip the coil around and it was facing away from me. And that kind of, like I said, it was embarrassing to say the least, but whatever, it worked. I got, I saw my problem. I fixed my problem. No one else had to find it for me. I found my problem. I fixed it. System worked, passed the HERS test, passed inspection. Everything's good. So that is my story about the horizontal left versus horizontal right. just before you complete your install, when you're in the process of, kind of mapping out what you want to do with your system, where you want to put things, make sure you are aware of which way, if you have a horizontal left or a horizontal right system, so you can know which way you want to install it before you have to redo something. Okay, so then you got tube in a tube type of, so these are chiller evaporators. You have tube in a tube evaporators, or you have shell and coil, or shell and tube. So this is the most common that I've seen on large chillers, where there's just this big shell and then there's tubes going through it with chilled water in those tubes. So that whole tank is full of refrigerant, and then there's tubes of water going through there, and that water is what's absorbing heat and taking it back to the cooling tower, and then cooling it and then coming back in it. So that's how the shell and tube works. The tube in a tube, there's refrigerant inside of the copper tube, and then there's water inside of the tube around the copper tube, and that's what's cooling the refrigerant. So there's different types. And then you have the shell and coil, where, same thing. You got the refrigerant going through the coil. But so evaporator design is specific to the intended application. An evaporator that performs perfectly in one application might not work all that well in a different application. And that's all done by engineers that design these systems. They kind of determine, the capacity of these systems, or what would be ideal applications for the different systems. Direct expansion evaporators. Most air conditioning and refrigeration systems use direct expansion evaporators, in which the refrigerant travels through tubing. It enters as a saturated mixture and leaves as a superheated vapor. The refrigerant that enters these evaporators is a mixture of liquid and vapor. So that's that 75% flash gas that we talked about, where there's the moment that the liquid refrigerant passes through the metering device, which is directly before the evap coil, 25% of that refrigerant flashes into a gas. So you have 75% liquid, 25% gas. They call that flash gas. That's what's going into your evap coil. But by the time it comes out, if your charge is correct, if your system's performing correctly, it should be 100% superheated vapor coming out of your evap coil. Evaporator construction, 3 common types: bare pipe, plate, tube, and fan coil. So those are those 3 types again. So bare pipe. Bare pipe evaporators are used in domestic upright freezers. The evaporator tubing also serves as the freezer shelves. In commercial refrigeration, bare pipe evaporators may be used for low temperature refrigeration, liquid cooling, ice skating rinks, and thermal storage applications. Plates are a special form of extended heat transfer surface used in refrigeration and freezer applications. The plate surface can be fabricated in a variety of shapes. Many plate evaporators are used in small residential refrigerators. Under the counter refrigerators do not defrost automatically. When manually defrosted, these units, individuals often puncture the evaporator. Why can't I see this today? Sorry. So when manually defrosting these units, individuals often puncture the evaporator refrigerant passages with sharp metal objects. So yeah, it's not a good idea to scrape on them with, to try to scrape the frost off with a tool or something. The best way to do it is to just turn it off and let the ice melt. Or I remember back in the day when our refrigerator defrost wasn't working, and moms used to have to ever so often just empty the freezer out and put a pot of boiling water in there and close the door and just let everything melt. So that's one way of doing it too. So tube and fan coils. The most common evaporator for cooling air is the tube and fan coil. Fins are added to the copper tubing to increase the surface area. Fin spacing. The distance between fins is called fin spacing, or fin pitch, and is expressed as the number of fins per inch. The fin spacing on low temperature coils can be 1 to 4 fins per inch to reduce ice bridging. Ice bridging is the term for what happens when the ice on one fin joins up with the ice formed on the adjoining fin. It restricts all airflow through the coil. So basically, on low temp applications, the fin spacing would be a lot wider than on high temp refrigeration, and that's to prevent the bridging, because frost is going to form on low temp applications. That's just part of it. But so they allow for that, but they don't want too much of that to happen, because then the ice will start to form a bridge with the ice on the in the next channel, and eventually that bridge will create an entire blockage, and it'll kill off your airflow. You'll just basically have a slab of ice, and now you're not moving any air across that coil. Now you're risking your system. Tube and fin coil tubing. The number of refrigerant tube rows in each refrigerant circuit and their spacing has a great influence on heat transfer in fan coils. Grooves inside the tubing help to churn the liquid refrigerant to the sides of the tubing for greater heat exchange capabilities. The number of refrigerant tubing rows can range from 1 to 10. Another improvement is to make tubing oval shape to help increase surface area. The thickness of fan coils greatly affects the coil's heat transfer and air resistance. Fan coils range in thickness from 1 inch to about 1 foot. Residential and light commercial air conditioning coils range from 1 inch to about 4 inches thick. Commercial refrigeration coils may be up to 12 inches thick. Typical air conditioning evaporator operation. Coil temperature is typically 30 to 40 degrees below the return air temperature entering the coil. Temperature drop across the coil is usually between 10 to 20 degrees. Standard airflow is 400 CFM per ton. For years, the standard design for evaporator saturation temperature was 40 degrees Fahrenheit at ARI rating conditions. The standard ARI rating condition includes 80 degrees Fahrenheit dry bulb and 67 degrees wet bulb return air. Many manufacturers are now designing the evaporator to operate at 45 degrees Fahrenheit under the same conditions. Air conditioning condensate. Direct expansion coils operating below the dew point will cool the water vapor and the air passing across it and form water droplets. It is drained by gravity into the drain pan and flows through a condensate drain line to the drain or sink disposal. Failure to properly design a draw-through condensate trap will allow the negative pressure in the coil drain to stop the condensate from draining. Excessive condensate will then overflow in the drain pan, which can cause damage to the structure. So you have to have basically, they call it a vent. You have to have your P-trap and then your vent. And all that is just a little piece of pipe to allow air to flow. But then also the P-trap is important. They don't mention it here, but the P-trap is also important because that water that collects in the trap also acts as a plug to prevent sewer gases from coming back into the system and smelling up the home, because that can happen depending on where your drain is connected to. It can be connected to a dedicated drain line that actually does go to the sewer, or in a lot of cases in residential, like air conditioning, the drain will just go out into the backyard. But you do have to have your vent and your trap. Evaporator coils can be arranged in multiple circuits and refrigerant flow controlled by solenoid valves. The circuits can be in separate rows, or the coil face can be circulated in 2 sections. Capacity control adds efficiency to systems. but the fan speed cannot simply be slowed down as a means of capacity control. This is because as the fan speed slows, less heat is picked up by the evaporator. Therefore, the evaporator coil temperature can decrease below the freezing point. So you don't want to just modulate the airflow alone. The refrigerant flow has to be reduced as well to keep things balanced, or else you're going to start getting into really low temperatures and pressures, and then possibly send liquid back to your compressor, and that's a no-no because you will break your compressor. Types of defrost. Frost buildup acts as an insulator and inhibits heat transfer. Medium temperature cases defrost naturally on their off cycles, while low temperature cases must use electric, hot gas, or air to defrost. So hot gas bypass defrost would be instead of sending the discharge gas from the compressor to the condenser like normal, there'll be a valve that will shoot that discharge gas straight to the evap coil instead, and that hot gas flowing through that coil will melt all the ice on the outside. And then the electric defrost is literally these big giant wires that are installed throughout the evap coil, and they heat up and melts the ice. Almost like a toaster, how you have those little wires that go through and they glow orange and they get really hot, except these are a little different. They're insulated. They don't glow orange. We're not trying to ignite anything or like toast anything. We're just trying to melt some ice. So it's similar, but different. Drinking water fountains. Water fountains are shell and coil evaporators. The evaporator consists of a small storage tank cooled by an external coil of tubing wrapped around the tank and insulated with a styrofoam cover. Oversized evaporator and high loads. The effect of an oversized evaporator and a system operating with a high load are similar. In both cases, there will be more heat entering the refrigerant and the evaporator temperature will be high. Undersized evaporators and low loads. The effect of an undersized evaporator and a system operating with a low load are similar. In both cases, there is less heat being transferred to the refrigerant, and the evaporator pressure and temperature will be low. Restricted airflow can be caused by any of the following: dirty evaporator coil, dirty air filter, bad blower motor, ice on the coil. So you definitely don't want any of those things. Those are considered low load conditions, because the load on the evaporator in air conditioning, for example, is your return air. So if that warm air from the coming through the return is not quite making it across the coil at the rate that it should be, at least 400 CFM per ton. So if you have a 2-ton system, for example, you should be getting 800 CFMs of air across that coil. If that's not happening, that's considered low load, and then now you got issues. If there's that warm air from the return is the only thing keeping the condensation on that coil from freezing. So if you don't have that air, that condensation, eventually it'll start to freeze, and then you got a block of ice in there. So that could happen from dirty coil, a dirty filter, or the blower motor just not operating. Any of those things can cause low airflow, and if you're not moving enough air across that coil, then you're gonna have problems. So in summary, evaporators are manufactured for 4 broad types of applications: domestic refrigeration, commercial refrigeration, air conditioning, and chillers. So let me go ahead and close that. That is it for chapter 16. So I hope that was helpful. And like I always say, jump into your book, and because the book is going to go even deeper than this PowerPoint. But again, I hope that was helpful. The review questions are now on Flexi Quiz, so go ahead and get that done, and I will be seeing y'all later. All right.